Welcome you all in my next lecture. So in my last lecture I talked about like I didn't introduce the notions of Lagrange multiplier, but in my last couple of lectures I talked about like if I have a scalar field, in particular if I have functions from R to R, then there is a way to talk about or to find the points of extremum. Okay, so for that functions, how to find the extremum, that I have introduced or discussed. Then there is another problem like the constraint extremum problem. That means if I have a function from say Rn into R or some scalar field, and if I want to find the extremum of my function subject to some condition. So that is very important. So in that case, how we can solve that problem? So can the just usual method, just like getting critical points and investigating the Hessian matrix, will give you that kind of points of extremum, or I have to deal in a different way? The answer is yes, you have to deal in a different way. That is why Lagrange multiplier will come. Lagrange multiplier, I will introduce that one. Using that Lagrange multiplier method, you will be able to tackle those problems. So that's today's plan, to talk about Lagrange multiplier, and at the end I will talk about what is called exact differentials. Okay, so I'll start with the kind of notions of Lagrange multipliers first. Okay, so as I said, I should start with a constraint extremum problem, and then the kind of how I can handle those problems by introducing Lagrange multiplier method to solve those problems. Now what is that? I already discussed this slide in my last lecture. Okay, so if I constraint extrema for a functions from Rn to R or scalar field. So now earlier two examples, now you just think about that. Yes, the earlier two examples, that means if you remember, I have a functions from -2, -2 cross -2, -2, that interval to R with some nice functions. Again I have a functions, and I discussed that what will be the corresponding extremum values or global extremum, and the domain. Domain, I should say that where I am looking for this point of extremum, it's a triangle, right? One is a square, another is a triangle. Now if you think little deeply, that I can also realize those problem as a constraint extremum problem. Why? Because you see, when I have a functions and I want to extremize or get the extremum of those functions on some say interval, on like closed sets or the square or triangle, whatever it is, there is a boundary, right? And boundary consisting of finitely many lines. Now if you see that I already discussed that you have to see the interior points by just using or solving the partial differential equations, equating 0, get the point. So that is another way. Another point is that you have to look at the boundary. So in boundary there could be a possibility of having an extremum points of these functions. Now you see, if I have a point in the boundary, that means I want to have the kind of extremum of a, and that point lies in the boundary. Now boundary means what? For example, when I have that problem discussed about in the triangle, right? So that means if you have a triangle, that means if I have a points, if I want to find the points, possible extremum points, and suppose it lies in that boundary, that means it satisfies some equation, right? Like x plus y is equal to 9, if you remember, or say this one, I mean x is equal to 0. So that is, you can thought about as a constraint extremum problem, right? So that means I want to extremize, or I want to get the maximum, local maxima, local minima, global maxima, whatever it is, on this line, and line is a kind of equation. So that means it should satisfy, and that it should lies in that line, that means it should satisfy some equations along with the fact that it attains that extremum. So but point is that those examples are very simple examples. There you have a boundary, is because of course I am a function from R to R, boundary means it's a line, and of course finitely many lines are there. So therefore you can easily handle by keeping one variable fixed. You can think about it as a single variable, and you can do that. Now the question is, if I move from R2 to higher dimensions, your boundary will be not like that. Your boundary will be a little complicated, right? You have plane, you have a surface, very complicated boundary you will have. Now the question is that how to handle those situations. Suppose I have a function from Rn to R with some constraint that okay, g of x is equal to alpha, it will give you some surface, right? So now the question is how to handle those constraint maximum problems. So therefore you already have seen very simple constraint extremum problem. So now I want to deal with more general setting. Okay, so that is why this is one. So in earlier two examples, the boundary of the domains are lines in R2, very nice boundary. So now we want to discuss method to deal with more general boundary. More general boundary means I want to extremize my function shape subject to the condition g of x is equal to alpha, and that will give you a boundary, or what we call some surfaces, and there you have to deal with in a different way. So let U be a subset of Rn open, f and g two functions continuous. I want to maximize or minimize or extremize my functions f of x subject to the condition that g of x is equal to alpha. So as I said, so since I am dealing with constant extremum problem, so that means you have to be careful, like just solving partial differential equations, equating 0, get the point, that method will not work, and that is the example I have discussed. Suppose if I want to extremize, get the extremum values of these functions on this circle, then one can easily check that f attains minimum at the point 0 plus minus 1 and maximum plus minus 1 0. However, if I calculate the partial derivatives, first order partial derivative at the point 0 plus minus 1 and plus minus 1 comma 0, it is not vanishing. So therefore that method, whatever I have discussed in my earlier one, so that will not work. So that means I have to deal in a different way, and that is why Lagrange multiplier came into the picture. Okay, so that's why I have written test for constant extrema for a functions. Again, I am restricting myself from R2 to R. So later, of course, I will state a theorem from Rn to R, but let's understand explicitly what is the case in the particular case n is equal to 2. That means if I have a functions from R2 to R, that is more explicit because you have to just deal with first order partial derivatives fx and fy. So that is why it's much more explicit in this setting. So that's I have written as a theorem. It says that okay, if I have a functions f and g defined from some set u subset of R2 to R, it is C1. C1, you know, I have already discussed in my earlier lecture. C1 means 1 times continuously differentiable. That means derivative exists and derivative also continuous. Okay. So suppose that, so look at the statement of the theorem. Suppose that f has an extremum at the point AB in U such that g of AB is the value alpha, along with the fact that the gradient of g at the point AB is non-zero. So what are the assumptions I have? So I have two functions f and g, they are C1, number 1. F has an extremum at the point AB with the assumption that gradient of g at the point AB is non-zero, and I am suppose g of AB is alpha. Then what I am claiming is that then there exists a lambda in R which I call this as Lagrange multiplier such that gradient of f at AB is same as lambda prime gradient of g at AB. So that means what I am saying is that if I have a function f and g with the fact that f has an extremum at the point AB and g of AB is equal to alpha with the fact that gradient of g at AB is non-zero, then what I am saying is that gradient of f at AB, because what is the gradient of f at AB? It will be a vector in R2, right? Similarly, gradient of g at AB is also a vector in R2 because gradient of f at AB, which is nothing but del f del x at the point AB comma del f del y at the point AB. Similarly, gradient of g at the point AB means del g del x at the point AB comma del g del y at the point AB. So it's a vector in R2. So what I am saying is that if these things happen, that means if I have a functions which has an extremum at the point AB with the fact that g of AB is alpha and gradient of g at AB is non-zero, then there exists a lambda which I am calling it as Lagrange multiplier such that the gradient vector are parallel. That means gradient of f at AB, which is lambda multiple times gradient of g at AB. So that means this gradient vector, they are parallel actually. So I give a very simple proof. Actually, I am trying to written a proof of that. What I am doing is that proof is also okay because so I have a function g, right? So now let RT be the local parameterizations of the curve g of x is equal to alpha. So once I have a AB is fixed, so g of AB is equal to alpha, that alpha is fixed. So you consider the curve g of x is equal to alpha and take the local parameterizations of that curve in terms of RT I am writing such that the initial point R0 is the AB. So that means I have a curve in R2 whose starting point, that means R is a map from say closed interval 0 to some finite interval to R2. So at 0 it is taking the value A comma B and then you will have some curve. Okay, see the parameterizations of the curve g of x is equal to alpha with the local parameterization is R. Then what will happen? F is given nice. Now R is the local parameterizations. What you do? You compose composition function. That means F compose R of T. So it's a map from where to where? It's a map from R to R once again. R is a parameterizations. Okay. So F is given to be C1. R is a local parameterization. Again, I can think about it as a C1 function. So composition again is very nice function. Differentiable functions. In fact, derivative is continuous. Along with the fact that since f has an extremum at the point AB and R of 0 is AB, so therefore this composition function has an extremum at the point t is equal to 0 because R of 0 is equal to AB. So now I have a new functions f composed R which is a map from R to R whose evaluation at the point 0 is nothing but f of AB, and hypothesis of the theorem says that f has an extremum at the point AB. So that means what I am saying is that the function composition function f compose R, it has an extremum at t is equal to 0. Now once it has an extremum at t is equal to 0 and f compose r is c1, it's very nice function, differentiable, then what will happen? If I consider derivative at t is equal to 0, it has to be equal to 0. That is a necessary condition. If you remember, the necessary conditions for extremum at some interior point is nothing but the derivative exists and derivative has to be 0, right? So now since function is differentiable, in fact it is c1, so derivative exists, it is 0. So therefore d dt of f compose rt is 0. But what is this? d dt of f of rt by chain rule, because it's a composition function f compose r, it is nothing but the gradient of f at ab dot product with derivative of r at 0. So that by chain rule you can have it, right? So therefore what I observed is that given the hypothesis that f has an extremum at ab, I consider the curve g of xy is equal to alpha, where alpha is nothing but g of ab. Then I am taking the local parameterizations r, I am considering the function f composed r, and then I am saying that the function f composed r has an extremum at t is equal to 0, and therefore the derivative is 0, and therefore by chain rule I am saying that gradient of f at ab dot product with r prime 0 is 0. That is one hand. Another hand is that now since g of xy is alpha, that curve has a parameterization rt, so therefore g of rt is equal to alpha for all t, okay. Now once is this one, then you just take the derivative in both sides. So therefore, so now g is again, g is c1, r is c1, so composition function is very nice, c1 function you can go for the derivative. If I take the derivative in the left hand side, this is a composition function by chain rule, which is nothing but the gradient of g at ab. And then I am evaluating at the point 0, dot r prime as 0 is same as right hand side is alpha. If I take the derivative is a constant, is 0, so therefore 0. So I have two things happening. One thing is that if I assume that f has an extremum at the point ab, then by taking local parameterizations r of the function g of xy of the curve g of xy is equal to alpha, I am concluding that gradient of f at ab dot r prime at 0 is 0, and because r is a local parameterization of the curve g of x is equal to alpha, I will have gradient of g at ab dot r prime is 0. Now what will imply? So that means this will imply that r prime at 0 is actually orthogonal to this gradient vector, and this will implies r prime 0 is orthogonal to gradient of f at ab. So that means the gradient vector of f at ab is actually parallel to gradient vector of g at ab. In other words, this is same as some lambda times gradient of g at ab, and for some lambda belongs to 1. So that's what it says. So therefore, if I assume that I have a functions, two functions f and g, if my function f has a local I should not say, I have some extremum at a point ab with the fact that g of ab is alpha and gradient of g at ab is non-zero, then the gradient vector of f at ab is parallel to gradient vector of g at ab. So this is the theorem. So there is a test for constraint of extremum, okay. So now I have introduced the method of Lagrange multiplier. That means if I have a problem, constraint extremum problem, how to change to a unconstrained one and solve whatever I have discussed the method earlier. So this is the method. So to find, so I have written method of Lagrange multipliers. Again I am dealing with the functions from R2 to R. To find extremum of f subject to the constant g of xy is equal to alpha, what we have to do? I have actually, to handle that sort of problems, I have introduced the auxiliary functions L. So I am having a functions f from R2 to R and g from R2 to R, okay, but now I introduce an auxiliary functions L, which is a function of three variables, that means x comma y comma lambda. And what is that? This is f of xy minus lambda times g of xy minus alpha. So that means given that problem, you consider auxiliary functions which is a functions of one variable more, that means x y lambda, which is nothing but this one. And then what you have to do, you have to just solve this equation. So now you have a functions of three variable and assume that your function is very nice. F and g, suppose is c1, it's very nice, and it is lambda. Of course, I am just sitting with lambda. So in terms of variable x, y, lambda, my capital L function is very nice. In other words, partial derivative of L with respect to x, y, lambda exists. So that means if the first order partial derivative of lambda exists, suppose del partial derivative of L with respect to x, partial derivative of L with respect to y, and partial derivative of L with respect to lambda. So that means this first order partial derivative you have to calculate, you have to equate with 0, and you have to get the equations, right. That's what the earlier method says. If I want to find a problem, or if I want to extremize some functions, you just suppose your domain is nice, and if I want to find the critical points, and what you have to do, you have to just calculate the first order partial derivative, equate to 0, get a couple of equations and solve it. So exactly I am doing the same thing. So I am just starting with the functions f and g, two variable functions, then I am introducing a new function which I am saying is a auxiliary function, and then equating the first order partial derivative is equal to 0 will give rise these three equations. So partial fx is equal to lambda times gx, fy is equal to lambda times gy, and g of xy is equal to alpha. So now I have three equations. Okay, so I mean del f del x is equal to lambda times del g del x, del f del y is equal to lambda times del g del y, and g of xy is equal to alpha. Now the auxiliary function L x y comma lambda is called the Lagrangian, which converts the constant extremum to unconstant extrema. So that is important. Okay, so now I am starting with a constant extrema problem, then I introduce auxiliary functions to change my problem to a unconstrained extremum. Now you solve it. Okay, so now you have to find what you have to find the critical points, and you have to see on the behavior of the Hessian matrix and conclude that whether kind of extremum will exist at some points or not. Okay, so now critical points of L are eligible solution for constant extrema. So that means critical points of L is nothing but the eligible points for the extrema of the constant problem. Okay, so that's how the Lagrange multiplier will do. So that means if I have a constant extrema, what you do, you introduce new auxiliary functions which is one variable more, and you just solve the problem like the unconstrained one I have already discussed. That means you get the first order partial derivative, you will give the equations, get the critical points, and these are the possible points of the extremum of your constant one. Once I have some examples, then it will be more clear. Okay, so first example. So find the extremum values of this on the circle. Okay, so I am giving some what is called constraint. So that means the points should be in the circle. So now earlier one, what it says, you have three equations. So that means del f del x is equal to lambda times del g del x. So this is one. Then del f del y is equal to lambda times gy, and g of xy is equal to 1. This is the constant. Okay, you have three equations. You have to just solve it, right? So that means if I solve it, so first one will give you 2x is equal to lambda times 2x, second one will give you 2 minus 2y is equal to lambda times 2y, and third one is x square plus y square is equal to 1. You have to solve it just. Okay, so the first equation shows either x is equal to 0 or lambda is equal to. You have only two possibilities because it is 2x is equal to lambda times 2x. So if I take this one, what will happen? See, this should be x, if I take common, 1 minus lambda is equal to 0. So you have two possibilities, either x is equal to 0 or lambda is equal to 1. Now if x is equal to 0, then of course this equation will give you y is equal to plus minus 1, and once y is equal to plus minus 1, then x is equal to lambda, it will give you lambda is equal to minus 1. Okay. What about the possible solution x, y, lambda, which is 0, plus minus 1, minus 1 are possible solution if x is equal to 0. And if lambda is equal to 1, then you have y is equal to 0, and once you have y is equal to 0, then what will happen? This one will give you x is equal to plus minus 1, and then you have the possible solution is x, y, lambda is equal to, first component is plus minus 1, second is 0, and third one is 1. These are the possible solutions. So these are the possible solutions of these equations, what I just introduced in the from constant to unconstrained one. Now you have to just evaluate. So now look at, these are the possible points. So first one is x coordinate, second one is y coordinate, third one is lambda coordinate. But I want a point in the two variable x, y. So you just forget about the last variable, think about the first two variables. So that means you just concentrate on 0, 1 and 0, minus 1, and 1, 0 and minus 1, 0. And you can get the value of these functions. So these 2 points it give the value minus 1, and these 2 points it give the value 1. So that the minimum and maximum values are minus 1 and plus 1. Okay. So that's very nice actually. So that means if I want to handle this kind of problem, you just make a auxiliary functions L x y lambda, which is nothing but f of x y minus lambda times g of x y minus alpha. Here g of x y is equal to x square plus y square, and alpha is equal to 1. Get three equations, get the solutions, and just see the value of the functions. Okay, that's what it will give you. So these are at least the possible points. It will give you the possible points where you can look for the extremum values of f, whether maxima or minima. Another example, okay, I have given. So okay, find the extremum value of these functions. Again, whatever functions I am dealing with, very nice functions, is actually polynomial. So it is differentiable. That means first order partial derivative exists, second order partial derivative exists, they are continuous, everything is there, subject to the condition that this is 0. Again, do the same process. So that means what you have to do. So that means fx is equal to lambda times gx, fy is equal to lambda times gy, and g of xy is equal to 0 or alpha. That three equations will be there. So that means this is the equations actually. Gradient of f at x, which same as lambda times gradient of g at x, and this is the gradient vector you already calculated. That means this is nothing but del f del x at the point xy, and what is this? This is del f del y at the point xy. Similarly, this is del g del x at the point xy, and this is del g del y at the point xy. Okay. So now if I have any points, you have two equations. So first equation this, that means this is del f del x is equal to lambda times del g del x, and this is del f del y is equal to lambda times del g del y, and this is u of x y is equal to 0. That means you have one equation, two equation, three equations. You have to just solve it. If I solve it, then solving we get two solutions. I am not doing the kind of rigorously this part. You should solve it. You have very three simple equations. You should solve it. If you solve it, then these are the possible solution you will get. Lambda is equal to 2, x is equal to 1, y is equal to minus 1, and for lambda is equal to 0, you have x is equal to minus 1 and y is equal to 1. So that means you have possible solutions x, y, lambda. Now you just focus on x and y coordinates. So that means you have to just look for the point 1, minus 1 and minus 1, 1. Now at 1, minus 1, the functions attain maximum value, and at minus 1, 1, the functions attains minimum value. And that you can just evaluating the functions at this point, then it will be able to see. So that's what you can handle those kind of problems. Okay. Okay, another examples. Okay. So find the extremum values of these functions subject to the condition x, y minus 1 is equal to 0. Okay, again we have three equations. Del f del x is equal to lambda times del f del g del x, del f del y is equal to lambda times del g del y, and g of x y is equal to 0. So first one give you this equation, second this one, and x y is equal to 1. You have three equations, and then if you solve it, then I think you will have this is the solutions, because easy. For example, if you multiply these two, what will happen? This should be actually 4 times xy, which is exactly equal to lambda square xy. Xy is equal to 1 given. So that means what? Lambda square is equal to 4. So what will implies? That means lambda is equal to plus minus 2. Once you have a lambda is equal to plus minus 2, that means then this which will give you actually two possibilities, either x is equal to 1, y is equal to 1, x is equal to minus 1, y is equal to minus 1. Because you have lambda is equal to plus minus 2. If you put lambda is equal to 2 here, that means whatever, 2x is equal to 2y. That means, okay, both things. That means x and y has to be same, right? So therefore, x is equal to 1, y is equal to 1. That will come because of this fact, and similarly you have these possibilities. And once I have that x, y, lambda, possible values x, y, lambda, you just forget about lambda, think about that x and y. So that means you have to just 2 points at 1, 1 and minus 1, you have to consider, and you can check that f attains maximum value at 2, maximum value, f has a maximum value, attains its maximum and value is 2, and at minus 1, 1 it attains maximum and value is 2. So that's how we have to handle. Okay, another example again. So find the greatest and smallest values of this functions f of x y is equal to x y takes on the ellipse. So this is the constant problem subject to the condition, right? Again do the same process. F x is equal to lambda times g x, f y is equal to lambda times g y, and g of x y is equal to alpha, in this case 1. That means you have these three equations 1, 2 and 3, and you have to solve it. So again it gives that, I am not giving the full solutions for that, but I am giving a hint here. So if you solve it, because these are three simple equations, so you will be able to conclude that, okay, so I think these two implies, this two maybe implies y is equal to lambda square by 4 times y, which will have two possibilities, y is equal to 0 or lambda is equal to plus minus 2. Now if y is equal to 0, then x has to be is equal to 0 because of these equations, okay, but which is not possible because it has to satisfy this constraint equation as well, because this is x square by 8 plus y square by 2 is equal to 1, which is not the case. So therefore 0, 0 you can rule out, okay. So which is ruled out the case because 0, 0 does not lie on the ellipse. So what are the possible points? The possible point is 2, 1, minus 2, minus 1, 2, minus 1 and minus 2, 1. You have 4 possible points where you can have the greatest and smallest values possible, okay, and you just evaluate like at 2, 1 and minus 2, and if you see the functions attain maximum value, and 2, minus 1 and minus 2, 1, the functions attains minimum value. So that's how the Lagrange multipliers plays a role, okay. Okay, so now I am saying again once again that's combining thing is that finding global. So this is global extrema for functions from R to 2R subject to some conditions. How to handle that situation, I have just written the process step by step. Okay, so let F is a map from R to 2R, U is a subset of R to be a region with smooth closed boundary curve C. So suppose this is a region which has a smooth closed boundary, let it be denoted by C. Then to find the global extremum of F in U, what we have to do? First we have to locate all critical points of F in U, okay. That means interior, you have to first get the critical points inside U, and then find eligible global extremum of f on the curve. You see, on the curve we have to also see. So inside you can do it, right? Inside the domain, that means in interior point, that means you just perform the partial derivatives equate to 0, you will get the critical points. But since it has a smooth boundary, closed boundary, that means in the boundary point also you have to see, and that boundary points, when looking at the points which might be a possible points of extremum, that means that subject to the condition that it should be in the boundary, that will give you the constraint extremum problem. So find eligible global extremum of f on the curve C by using Lagrange multipliers or parameterizations. So that means if I want to see the points which possibly extremize my function subject to the condition that it should be in the boundary, that means I am having a constraint extremum problem and I need a Lagrange multiplier to handle that situation. Okay. So now third one is that choose points among eligible solution in C and the critical points at which f attains extreme. So that means, so points inside C, that means interior, that means critical points, and on the boundary points, whatever the points, you just collect it and evaluate your function and see whether my functions attain maximum or minimum. So these extremum values are the global extremum. You have to just look at and then conclude that global extremum. Okay, one example I have given global extremum. For example, find the global maxima and global minima of the functions f of xy is equal to x square plus y square by 2. Again, it's a function of xy, very nice functions in this domain. So that means x square by 2 plus y square by 1 lesser equal to 1. That means I have a circle, okay, circle with the boundary is x square by 2. This is boundary. That means x square by 2 plus y square is equal to 1. Inside I am talking about including the boundary. So that means you have to find the critical point inside, along it you have to deal with the boundary case. So look here. So that means if I look about the interior points, you just make the partial derivative of your function fx, fy equate to 0 and get the solution in there. So that means 0, 0 is the only critical point in the interior. Now you have to look at the boundary. So now consider to deal with the boundary case, that means I want global maxima or global minima, that means I want to extremize my functions f subject to the condition that xy should be in the boundary. That means it should satisfy the equation 1. So that means it is a constraint maximum, right? Now I have to use what is called Lagrange multiplier. So now to handle the point in the boundary, you have again the same I already discussed, introduce a Lagrangian, which is L of xy lambda, which is nothing but f of xy minus lambda times g of xy minus 1. Okay, and then Lagrange multiplier equation give you 3 equations, fx is equal to lambda times gx, fy is equal to lambda times gy, and g of xy is equal to alpha, that means here actually 1, 3 equations, you have to solve it, that is it. So if x is equal to 0, then y is equal to plus minus 1 and lambda is equal to half. Now if y is equal to 0, then you will have possibilities x is equal to plus minus root 2 and lambda is equal to 1, but you have to be careful. I want that if xy is non-zero, then lambda is equal to 1 and lambda is equal to half, which is not possible, and that is straightforward. Why? Because you see, what are the that's the solution you have to do. So if x is equal to 0, then you will have y is equal to plus minus 1, right, and lambda is equal to half. So these are this one case. If x is equal to 0, then we will have y has 2 possibilities, lambda is equal to half, and if y is equal to 0, then you will have x is equal to plus minus root 2 and lambda is equal to 1. Now if xy is non-zero, which I want, right, because if xy is equal to 0, that means one of them is 0, so that means it will contradict the fact that this y has to be yes. So what I am saying is that if xy is non-zero, then you will have lambda is equal to 1 and lambda is equal to half, which is not possible. Why? That is very nice one. Because you see, look at the equations. So x is equal to lambda x and y is equal to 2 times lambda y. So if I have this one, that means x comma 1 minus lambda is equal to 0, right. So therefore you will have, if xy is non-zero, that means lambda is equal to 1 and lambda is equal to half. I am saying that which is not possible. Why? Why is that? Because what is my lambda? Yeah, okay. So I have 3 equations, x is equal to lambda x, y is equal to 2 times lambda y. So that means what I will have, so this is 1, this is y is equal to 1 minus 2 lambda is equal to 0. So if xy is non-zero, so that means x is non-zero, y is non-zero, then that will give you what? That means I will have lambda is equal to 1 and lambda is equal to half. So okay, so I have these functions, then the Lagrange multiplier equations give you 3 equations, x is equal to lambda x, y is equal to 2 lambda y, and it has to satisfy this. That is very important actually. X square by 2 plus y square is equal to 1. Okay, so if x is equal to 0, then we will have y is equal to plus minus 1, it follows from here, and y is equal to plus minus 1. If I put y is equal to plus minus 1, then lambda is equal to half it will give. And if y is equal to 0, then you will have x is equal to similar way and lambda is equal to 1. So, two possibilities. So, if x is 0, y is 0, and if x, y are both non-zero, then what will happen? If x, y is non-zero, then again lambda is equal to 1, lambda is equal to half. Now, if lambda is equal to 1 and x, y is non-zero, then what will happen? So, what I am doing is that suppose if x, y is non-zero, then what will happen? So, what are the possibilities? Either x is 0 or y is 0, or both of them are non-zero, right? So, if one of them is 0, it will give you x, y is equal to 0, right? So, now if x is equal to 0, then I will have y is equal to plus minus 1 and lambda is equal to half, right? And if y is equal to 0, then x is equal to plus minus square root of 2 and lambda is equal to 1. Now, if x, y is non-zero, that means x is non-zero, y is non-zero. That means it has to implies these two equations, you have lambda is equal to 1 and you have lambda is equal to half. Okay? Now, if I have lambda is equal to 1 and lambda is equal to half, then I am saying that which is not possible. So, what I am saying is that, okay, now clear. So, x is equal to 0, then it perfectly all right, y is plus minus 1 and lambda is equal to half. And if y is equal to 0, then x is equal to plus minus root 2, lambda is equal to, that is perfectly all right. Now, you see if x, y is non-zero, then from these two equation it will implies lambda is equal to 1 and lambda is equal to half, right. Now, once I have two values, lambda is equal to 1, so now lambda is equal to 1, that x is equal to x, that part is perfectly all right, because if I put lambda is equal to 1 here itself, right, then what will happen? 2y is equal to y, then y is equal to 0, which is not the case because I assume x, y is non-zero. That was the catch actually, yes. So, therefore, if x is equal to 0, then y is equal to 0, then you should get the value. But whenever x, y is non-zero, then I am having two possibilities of lambda, either lambda is equal to 1 and lambda is equal to half, right. In any cases, it will implies because of these two cases that one of x has to be 0 or y has to be 0, and that will give the contradiction that x, y is non-zero. Suppose this is not possible, that is what I have written, yes. Now, it is clear. So, therefore, what are the possible solutions? You have the only possible solution is that either x is equal to 0 or y is equal to 0. Now, if we ignore the lambda, so that means 0 plus minus 1 or plus minus root 2 0 are the eligible solution in the boundary curve. And if you just evaluate it, f evaluated at 0 comma plus minus 1 is equal to 1 by 2, f evaluated at plus minus root 2 comma 0 is equal to half, and f of 0 0 is equal to 1. Okay, clear? So, therefore, you have three equations and you have to solve it. So, if x is equal to 0, you will have something, if y is equal to 0, you have something, but if x, y is non-zero, then you will have a contradiction because you will have two possibilities, either lambda is equal to 1 or lambda is equal to half. Now, if I take lambda is equal to 1, then this equation will give you that y is equal to 0, and if I take lambda is equal to half, then this equation will forces you to conclude that x is 0, which is a contradiction to the fact that I assume that x, y is non-zero. So, therefore, this case is not possible. So, only possibilities is that either x is equal to 0 or y is equal to 0. So, therefore, these 2 points are eligible solutions on the boundary curve, and you just evaluated the value, and then you will have the global maxima and global minima. Okay. So, now I think bit clear you have. So, that means therefore, if we have a problem like we want to extremize or to find a global maxima and global minima on some domain. So, in the interior you just do the partial derivatives, equate 0, get the critical points, and you can think about, okay, you can conclude again depending on the points that, okay, whether it is global maxima or minima, extremum, I think, in the interior. But in the boundary, you will have to be careful, because in the boundary, that means I want possible points where extremum exists, but it has to satisfy the condition that the point should be in the boundary. That means some constraint is there. And once I have a constraint, then you have to handle in terms of Lagrange multiplier, and again you get the possible points where you will have the extremum will exist, and you have to just analyze and you have to just conclude it. Okay, so this is actually the test for constraint. Earlier I have a statement from R2, now you have a R into R. What it that says? So, let f and g, you have functions u subset of R into R, which is C1, again 1 times continuously differentiable, that means derivative exists and derivative is continuous. Suppose f has an extremum at the point x naught is in u, g of x naught is the same statement, whatever I have done for R2 to R, same R into R. So, suppose f has an extremum at the point x naught, g of x naught is alpha, gradient of g at the point x naught is non-zero, then there exists a lambda such that gradient vector of f at x naught is parallel to gradient vector of g at x naught. That means, gradient of f at x naught is lambda times gradient of g at x naught. Then, if g of x is equal to alpha is a closed surface, then the global extremum is obtained by finding all points where this gradient of f(x) is equal to lambda times gradient of gx, and choosing those where f is largest and smallest. So, that means same thing. So, you have to have three equations, like one is that equation will come from gradient of f at x is equal to lambda times gradient of g at x, along with the fact that g of x is equal to alpha. You have three equations, and those points, whatever the points you will get, and these are the possible points where you will have, you can choose where f is largest or smallest. Or Lagrangian, in terms of Lagrangian, the Lagrangian is given by Lx lambda, fx minus lambda times gx minus alpha. So, the multiplier equations, this will give you the system of equations, and you have to solve in terms of capital X and lambda. Now, you just, once you have the possible solution, ignore the lambda, whatever the possible points x will get, and those points you have to analyze whether global or extremum, or whether the extremum exists or not. Okay, one example I have given. Okay, so I am saying that maximize the functions f of x, y, z, which is x plus z, subject to the constant x square plus y square plus z square is equal to 1. Again, you have to consider the multiplier equations. Again, L x y lambda, I think this time 3 variable, right? So, that means L of x comma y comma z, I mean this function L of x comma y comma z comma lambda is equal to f minus lambda times what will happen g. So, this is my function g of x y z. So, that means g minus 1. So, if I do, so that means how many equations I will get? 4 equations I will get. So, this is fx is equal to lambda times gx, fy is equal to lambda times gy, and fz is equal to lambda times gz, along with the g of x, y, z is equal to 1. So, if you solve these 4 equations, so from first and third equations, you can conclude that lambda is non-zero. Then by second equation, you can conclude that y is equal to 0, and by first and third equations, you conclude that x is equal to z. So, therefore, x is equal to z is equal to plus minus 1 by square root 2. So, therefore, what are the possible solution? This is the solution. X naught is equal to 1 by root 2, 0 and 1 by root 2, because you can ignore the lambda part, and x1 is equal to minus 1 by root 2, 0, minus 1 by. These are the eligible solutions, and this shows that you have to just evaluate your functions at that point. So, this will give you square root 2, and this will give you minus root 2. So, this is the maximization. So, that is how you have to handle those kind of problems. Okay, till now I have discussed constraint problem with one constraint. Now, question is, if I have say multiple, like m many constraints, then how to handle that situation? Same method will work. So, that is why I written extremum problems with more than one constraint. So, find the extremum values of the functions, these functions f d subset of R into R, subject to m constraint. That means g1x is 0, g2x 0, and gmx 0, where m is strictly less than n. So, that means I have n variable, I have m constant, m is strictly less than n. Now, how to handle? So, similar way I can handle. So, this problem can be solved using the method of Lagrange multipliers method by introducing m Lagrange multipliers lambda 1, lambda 2, lambda m. That means, when I had a like one constant, then I have a one Lagrange multiplier. Now, if I have m constant, we have to introduce m Lagrange multipliers. Okay. So, we find a point C, C1, C2, Cn, and lambda 1, lambda 2, lambda m, which satisfy the following m plus equation simultaneously. So, that means earlier you will have just whatever variables you have plus 1. So, now you have a m constant. So, that means you have a lambda 1 plus lambda 2 plus lambda m. So, that means you have a m plus 1 equation we will have. So, that is what. So, how do you get it? So, this is the one. First, gradient of f at any points, you have to just introduce m Lagrange multipliers, and you have to consider this equation, lambda times gradient of g1 plus lambda 2 times gradient of g2 plus lambda m times gradient of gm. So, earlier you will have only gradient of f is lambda times gradient of g. Now, this times if I have m many constant, so you have to introduce m many Lagrange multipliers, and you have to consider the equations gradient of f is equal to lambda 1 gradient of g1 plus lambda 2 gradient of g2 up to lambda m gradient of gm, and you have these many constants are there, g of gkx is equal to 0, that means k is equal to 1 up to m. So, that means whatever constant you will have, how many constants g1, g2, gm plus 1, and plus 1 is coming from these equations. Okay. So, these many equations you will have, of course, depending on the variable you will have something here. So, therefore, these many equations you will have, and you have to find a point which satisfies all this along with this. So, that means we have to find a point C and lambda 1, lambda 2, lambda n that satisfies m plus 1 equations, this m plus 1 equation simultaneously, that is important, and that will give you the possible points of what is called extremum. Okay, one example I have given. So, look, in R3 we have a plane x plus y plus z is equal to 1, which cuts the cylinder x square plus y square is equal to 1 in an ellipse. Now, what I want, find the points on the ellipse that lie closest to and furthest from the origin. So, that means this is a problem, extremum problem subject to two constraints, if you remember. So, I want the plane cuts the cylinder in an ellipse, okay, and find the points on the ellipse that lie closest to and farthest, that means maximum distance and minimum distance from the origin. So, that means first step is to find the extremum values of these functions f of x, y, z is equal, you can transform into the constraint extremum problem subject to two constraints. So, that means I want to extremum values of these functions f of x, y, z is equal to x square plus y square plus z square subject to the constraint what? It should lie in this cylinder x square plus y square minus 1 is equal to 0 and this plane, right, g2 x y z is equal to x plus y plus z minus 1 is equal to 0. So, that means I want extremum values of this function subject to these two constraint. Okay. So, now you just apply the earlier theorem, earlier method, whatever I just said. So, that means you have one equation is that gradient of f is lambda 1 times gradient of g1 and plus lambda 2 times gradient of g2. It will give you this and these equations. Along with you have of course that constant equation is there, that means g1 of x y z 0 and g2 of x y z 0. So, that means these equations are there. So, therefore, if I do that one, you will have these equations you will get, and it will, of course, I am not telling you the full solution or rigorous solutions, but if you do that, just applying the earlier method I have discussed. So, it gives the possible solutions. So, lambda 1 is equal to 1 or x is equal to y with lambda 1 not equal to 1. I have just written we get solutions as these are the possible solutions, right. You have to just ignore lambda 1, lambda 2 and focus on x, y, z. So, we will have possible solution 1 0 0 0 1 0 1 by root 2 1 by root 2 1 minus root 2 p4 minus 1 by root 2 comma minus 1 by root 2 1 plus. So, these are the possible solutions. You have to solve it, and if you do it explicitly, you will be able to solve. These are the possible points. And what about the step 3? So, at p1 p2, if you just evaluate your function, the functions f attains its minimum value 1 and both of them are closest to the point to the origin, and at if you check p3 and p4, the functions f attains maximum value, however p4 is the furthest from the origin. Okay. So, that is one of the easiest example of a problem, extremum problem subject to more than one constraint. Okay. So, that means you will have to apply, just you have to perform these equations along with this constraint. So, these are the equations and you have to just find the solutions which satisfies these things, and then at the end you lambda 1 lambda 2 you have to ignore, focus on x y z. These are the possible points you should look for and you have to find the solutions. Okay, so I think that's all about like how to handle constraint maximum or constraint extremum problem using Lagrange multipliers. Now I am discussing at the very end that what is exact differential. That is the only last part is remaining. So, total differential, what is that? So, if I have a function f from some set d subset of R2 to R, suppose you have a function f which has continuous first order partial derivatives in that domain. Continuous first order partial derivative means partial derivative exists and they are continuous. Then the total differentiation or total differential, I denote it as d of f of a function f, which is defined as del f del x times dx plus del f del y times dy for all x y. So, if my functions has a continuous first order partial derivatives, then I am introducing the notions of total differential, which I denote it as d of capital F, and which is nothing but del f del x times dx plus del f del y times dy. So, one example I have given. So, if I have f of x y is equal to x y square plus 2x cube plus 2 times x cube y. This function is very nice. All order partial derivatives, in particular first order partial derivative exist and they are continuous. Then what will be the total differential? You just make the partial derivative of capital F with respect to x variable, calculate the partial derivative of capital F with respect to y variable, and it will be easy. Keeping one variable fixed, keeping y is fixed, think about a function of single variable x, perform the derivative. Similarly, keeping x is fixed, think about it keeping x is fixed and think about it as a function of y variable, perform the derivative, and this is the corresponding total differential. Once I have the notions of total differential, then I can introduce the notion of what is called exact differential equation or exact differential. So, what is exact differential? The expression mxy times dx plus nxy times dy is called the exact differential in a domain D if, so that means I have a expression mxy times dx plus nxy times dy, I will call is an exact differential in some domain D if there exists a functions capital F defined on that domain D subset of R2 to R such that m can be written as or m can be obtained, I should say, n can be obtained as a first order, as a partial derivative of capital F with respect to x variable, and n can be obtained as a partial derivative of f with respect to y variable. If these things happen, then I will say that this m dx plus n dy is an exact differential. Okay. So that means I have a function m dx plus n dy, I will say that it is an exact differential in some domain D. If m, there exists a function capital F from that domain D subset of R2 to R such that m is nothing but the partial derivative of f with respect to x variable and n is nothing but the partial derivative of f with respect to y variable. So this is called exact differential, and there is another definition of first order ODE. ODE stand for ordinary differential equations. So first order ODE, which is nothing but m dx plus n dy is equal to 0, is called an exact differential equations in a domain D if the object m dx plus n dy is actually exact differential, which I just defined in my last definitions. Okay. So this one, if I have a first order ordinary differential equation m dx plus n dy is equal to 0, then I will say that is an exact differential equations in a domain if m dx plus n dy is an exact differential. That means there exists a function f from domain D subset of R2 to R such that m is nothing but partial derivative of capital F with respect to x and n is nothing but partial derivative of capital F with respect to y. One example I have given. So suppose this is the first order ordinary differential equation y square dx plus 2x dy is equal to 0 is an exact differential equation R2. Why? Because if I consider this function capital F xy is equal to xy square, then you can easily calculate that y square is nothing but del f del x and 2xy is nothing but del f dy. So therefore this is an exact differential, and so therefore this differential equation is that exact differential equations. First order ODE. This is a first order ODE, first order ordinary differential equation. This is exact differential because this part is actually is exact differential. That means I have a function capital F whose the portion y square or m part obtained by partial derivative of f with respect to x, and this part n part obtained by partial derivative of f with respect to y. And this is the last one. Okay, so this is the integral curves of exact ODE. Suppose if I have an ordinary differential equation first order, so there is a notion of integral curves. It says that okay, start with the equation m dx plus n dy is equal to 0, which is exact in a domain D. So exact in a domain means what? So suppose if I have a equations m dx plus n dy is equal to 0 and it is exact in a domain D, that means the object, that means I should say that there exists a function capital F such that m is nothing but del f del x and n is nothing but del f del y, that I can have it, right. So if I have a equation m dx plus n dy is equal to 0 which is exact in a domain D, then I will have the existence of capital F such that this is and this is true. Now m dx plus n dy is equal to 0, so therefore the left hand side I can write, because m is this and n is this, so therefore this is nothing but del f del x dx plus del f del y dy is equal to 0. But del f del x dx plus del f del y dy, it gives the total differential, that means I can write it as d of f, right. So therefore this is, that means d of f is equal to 0. Now once you have d of f is equal to 0, you just have to integrate it. If I integrate it, then you have f of x y is equal to c, where c is an arbitrary constant. Okay. So therefore if I have a equation m dx plus n dy is equal to 0 and it is given that it is exact in a domain, that means you will have the existence of capital F such that d of f is 0, and therefore if I integrate it, I will have a solution f of x y is equal to c, where c is some arbitrary constant. Now once we have this one, then it defines a solution curve or integral curves of these equations. What is that integral curve? This is the integral curve, right. So f of x y is equal to c is said to be the implicit solutions of your ODE, that means mxy dx plus nxy dy is equal to 0. So that means if I have an exact ODE, that means if I have a first order ordinary differential equation given which is exact given, that means I will have the existence of capital F such that your m can be written as f del f del x and n can be written as del f del y, then you can make it to a total differential d of f is equal to 0. You have to integrate it, it will give you some curve f of xy is equal to f of xy is equal to c, and that defines a solution, I should say the implicit solutions of your exact differential equations, and that's sometimes called the solutions curve or integral curves. So that's very little about total differential. So that means if I total differential means it's very nice actually, that means I can have the solutions of ordinary differential equations, and total differentials means that means I have a nice functions, I can have the expressions of m and n in terms of the partial derivative of f with respect to x and with respect to y. Okay. So that's exactly I have written here. So it's exact differential. Okay. So m dx plus n dy is called exact differential if there exists a function such that these two conditions should satisfy. Okay. So I think I should stop here. So that's all about like maxima, minima, and then solving extremum problem, constraint, unconstrained one, and of course to solve the constraint one I need a Lagrange multiplier to kind of change it to unconstrained one and solve the problem. Then while solving that problem I have introduced the notions of critical points, then there is a notions of kind of there is a checking point, like there is a corresponding notion of a Hessian matrix, and by looking at the behavior of the Hessian matrix you will have the kind of conclusions that relative extremum or relative maxima minima exist. And then you have a global extremum, like if I have a domain with a boundary, then in the interior you have to check the critical points lying in the interior point, which are the critical points, along with the boundary you have to check. And more generally, if I am in higher dimensions, if a boundary means it actually constraint extremum problem, that you have to handle with Lagrange multiplier. And if you have finitely many constraints, that also you have to have a couple of equations, that means you have to introduce m many Lagrange multiplier and you have to solve it. And at the end I talked about exact differential, that means giving a solutions of the first order ordinary differential equation which are exact. I think that's all for today. In my next lecture maybe I will introduce, or I will start with a new concept called integrations in higher dimensions. Okay. For the timing I think I should stop here. Thank you.